Imagine a star that erupts like a cannon, firing invisible bullets across the Milky Way at 20 million miles per hour. These are not ordinary fragments from an explosion. They are knots of helium, launched from a rare stellar event that astronomers have now watched in extraordinary detail with the Hubble Space Telescope. Tonight, we are following those bullets back to their source, a peculiar binary system where two stars orbit so closely that one is slowly stealing the other's identity. The story is about a nova, but it is also a story about gravity, dead stars, and a strange recycling system that keeps a galaxy alive. This is the quiet cosmos. And our journey begins with a simple question: how can a star that is already dead create an explosion powerful enough to reshape its neighborhood? The answer starts with a white dwarf. A white dwarf is the dense leftover core of a star like our Sun after the star has exhausted its nuclear fuel and shed its outer layers. It may contain roughly the mass of the Sun, compressed into a sphere about the size of Earth. That comparison is difficult to feel until gravity enters the picture. On the surface of a white dwarf, gravity is hundreds of thousands of times stronger than on Earth. Matter does not simply land there. It is squeezed, flattened, and heated under immense pressure. Now place a second star nearby. In the system observed by Hubble, that companion is rich in helium. The white dwarf's gravity pulls gas from its partner, drawing a stream of material toward the compact star. Layer by layer, the stolen helium builds a thin shell on the white dwarf's surface. For a while, almost nothing appears to happen. The system may look like a faint point of light. But beneath that calm surface, the pressure and temperature continue to rise. The helium is being compressed inside an incredibly powerful gravitational vice. Eventually, the shell reaches a critical state. Helium fusion begins, but unlike the steady fusion in the core of a normal star, this reaction is unstable. The material cannot expand and cool quickly enough. The burning accelerates, and a thermonuclear flash sweeps through the accumulated layer. The result is a helium nova. It is not a supernova, and the white dwarf does not necessarily die. Instead, the surface shell detonates and is thrown into space. The event can brighten the system dramatically, while leaving the compact stellar core behind to begin the slow process all over again. What makes this particular system unusual is not simply that it produced a nova. Astronomers already know that novae occur when material accumulates on a white dwarf. The surprise is the way this helium nova appears to be firing discrete, dense knots of matter into the surrounding galaxy. Hubble's sharp vision allows scientists to separate the expanding debris into structures that resemble bullets. They travel through space at nearly 20 million miles per hour, carving through older material released during earlier outbursts. At that speed, a trip from Earth to the Moon would take only a little over a minute. But cosmic distances change our sense of time. The bullets are crossing a region around the star that is vast compared with any planetary system, and the light reaching us records a process that began long ago. The word bullet is a metaphor, but it captures something real. These knots are denser than much of the surrounding gas, so they can preserve their shape as they move outward. Shock waves form around them, heating the gas and making their paths visible. A shock wave is a moving front where gas is abruptly compressed. The compression raises the temperature and can make atoms glow at particular wavelengths. By studying those colors, astronomers can infer the chemical composition, speed, and history of the outflow. The bullets are not launched into empty space. The system has been shedding material for generations, creating a layered environment around the binary. Every new eruption encounters the remains of earlier eruptions, turning the region into a kind of archaeological record written in glowing gas. That record is one of the reasons novae matter. A single outburst may look temporary, but repeated events can enrich the interstellar medium with newly processed elements. The gas eventually mixes with clouds that form future stars, planets, and perhaps worlds with life. Stars are often described as furnaces, but they are also chemical factories. Inside them, simple elements are transformed into more complex ones. When stellar winds and explosions return those elements to space, the galaxy gains raw material for its next generation. The helium nova is especially interesting because helium burning follows a different path from the hydrogen burning that powers ordinary stars. Helium nuclei can combine to create carbon, and under the right conditions, further reactions can produce oxygen and other elements. A white dwarf therefore acts as both a vault and a pressure chamber. It stores material transferred from its companion, compresses that material, and then releases it in a sudden event. The cycle links the quiet physics of accretion to the violent physics of thermonuclear ignition. There is another mystery hidden in the jets. Why do the outflows form knots instead of a smooth shell? One possibility is that the magnetic field near the white dwarf channels the eruption. Magnetic fields can guide charged particles, creating narrow streams and uneven clumps. The binary orbit may also play a role. As the two stars circle one another, their gravitational interaction can shape the gas into preferred directions. A spinning, magnetic white dwarf inside a crowded envelope becomes a natural machine for producing asymmetry. Hubble images alone do not answer every question. They show the structure in visible and ultraviolet light, but astronomers combine them with spectroscopy and observations from other telescopes. Radio waves can reveal shocks, infrared light can trace cooler dust, and X-rays can expose the hottest plasma. Together, these observations turn a beautiful image into a physical experiment. The position of a knot can be compared across years to measure its motion. Its brightness can be tracked to understand cooling. Its spectrum can reveal whether it is helium-rich, metal-enriched, or mixed with older material. This is the power of time-domain astronomy, returning to the same object again and again. The universe changes slowly on human timescales, but repeated observations let us build a moving picture. Hubble is not merely taking a photograph. It is helping create a film of a stellar eruption. The expanding debris also reminds us that the night sky is not a collection of frozen images. Stars are born, age, collide, erupt, and fade. What looks like a still point of light may be the front edge of a shock wave expanding through millions of kilometers of space. Even the apparent violence is temporary. The bullets will eventually slow as they sweep up surrounding gas. Their energy will spread into the interstellar medium, and the sharp structures will dissolve into larger, fainter shells. The white dwarf may then settle back into relative quiet. Gas from the companion will continue to flow. The surface layer will begin building again. In the future, another flash may send a new generation of knots racing outward. That repetition raises a profound question about stellar evolution. Could systems like this eventually become something more catastrophic? If a white dwarf gains enough mass, or if the conditions inside it change, a thermonuclear runaway can destroy the star in a Type Ia supernova. Not every helium nova is headed for that fate. The balance between accretion, eruption, and mass loss is complicated. Some systems lose as much material as they gain, while others may slowly approach a critical limit. But these nearby eruptions give astronomers a laboratory for the same physics that appears in much brighter explosions. By studying the manageable version, scientists can test models of nuclear burning, magnetic fields, binary evolution, and shock formation. The cosmic bullets also help calibrate our understanding of distance and energy. Their motion can be measured directly, while their changing light provides clues about how energy moves from a hot eruption into a cold environment. And there is a human element to the discovery. The event is far beyond our reach, yet the laws operating there can be tested with instruments built on Earth and in orbit. A few photons captured by a mirror become evidence about gravity acting on a dead star. The photons have traveled across the Milky Way, carrying a message from a system that has been erupting for thousands of years. Hubble separates that message into shapes, colors, and motions. The result is a glimpse of matter in transition, from star, to explosion, to interstellar cloud. If we could watch the whole event in real time, it would not look like a single fireball. It would be a sequence of flashes, waves, knots, and fading shells. Each layer would tell us about a different eruption and a different moment in the binary's history. That layered structure is why the system feels almost like a cosmic laboratory slide. The past remains visible around the present. The newest bullets move through the oldest evidence, and the entire scene records how a star has changed over time. There is also a lesson in scale. 20 million miles per hour sounds impossibly fast, but the bullets still need years to cross their environment. The universe can combine extreme speed with extraordinary patience. A violent event can unfold inside a story that lasts far longer than civilization. The same is true of the white dwarf itself. Its final state was created by the death of a star, yet its story did not end there. In a binary system, a stellar remnant can become active again, feeding on a companion and producing new light. Death, in this case, is not a clean boundary. It is a transformation. The old star becomes a gravitational engine, and the material around it becomes a record of nuclear history. As astronomers continue monitoring the helium nova, they may discover that the bullets are arranged in patterns that reveal the white dwarf's magnetic geometry or the companion's orbit. Future observations could show how quickly the knots decelerate and how their shock waves evolve. New instruments will add more pieces. Infrared observatories can study dust and cooler ejecta. X-ray telescopes can follow the hot gas. Large ground-based telescopes can measure subtle changes in the spectrum. Each wavelength sees a different layer of the same eruption. And the story connects to a much larger question: how does the Milky Way recycle matter? The answer is not one dramatic event, but countless outflows from countless stars. Novae, winds, and supernovae stir the galaxy, seed new clouds, and move elements from one generation to the next. The helium nova is a small chapter in that enormous cycle. Yet its scale is exactly what makes it useful. A focused event can reveal the mechanisms that, multiplied across a galaxy, shape the material from which new systems emerge. So when you look toward the Milky Way, imagine that some of its faint light comes from a binary star quietly preparing another eruption. Imagine dense knots of helium moving through glowing gas, each one carrying information about gravity, nuclear fusion, and the long relationship between two stars. Hubble has shown us that the aftermath is not smooth and featureless. It is structured, directional, and alive with motion. The star has fired cosmic bullets into space, and those bullets are illuminating the invisible architecture around them. The final image is both dramatic and strangely peaceful. A dark field of space. A compact star hidden inside an expanding shell. Blue and violet gas, bright shock fronts, and knots racing outward into the night. The explosion will fade. The gas will disperse. But the elements released by that event may one day become part of something new: a cloud, a planet, an atmosphere, or an observer looking back into the dark. That is the quiet cosmos. Even a dead star can still send its history outward, one luminous bullet at a time.